Thank you all so much for coming. For those of you who don't know me, my name is Georgia, and Milo and I are two of the honors students in physics at Kenyon this year. And we were sad because the usual honors deal is that you do a public talk, but because that couldn't happen this year, and so Milo and I, because apparently we had too much time on our hands, we decided to organize our own shorter talks, and these are meant to be accessible, fun talks. So they're meant to be, we're telling stories about our research rather than telling you all of the little details. So we hope it's entertaining and you learn something. So Milo's gonna go first. So Milo Eder is from Shorewood, Wisconsin, and they have a major in physics and a minor in classics. They will be going to Ohio State University, OSU, in the fall for graduate school. And they're going to talk about, right now they're going to talk about the research they've been doing for the past, 2.5 years, almost 3 years, 2 years, with Professor Aaron Reinhard at Kenyon. Go for it.
So I'm going to be talking a little bit about a couple of the backbone aspects of my research that I've been doing here at Kenyon the last 3 years. So a brief outline of my talk before I start. My talk is going to be coming in 2 parts. For the first section, I'll be talking about Rydberg atoms. I'll explain what they are and a little bit about how we use them. Then I'll switch to be talking about laser cooling. I'll talk about what it is, a little bit of how it works, as well as like how we utilize it in our lab. And the photo on the right of this slide is actually a photo of our optics table. That is where the experiment happens. It's where all the magic and fun goes on. Every piece of equipment you see there was placed by hand, mostly by students. So that's my playground. So Rydberg atoms, what are they? Rydberg atoms are atoms with a high N, where N stands for the energy level of the atoms. It's also called the principal quantum number. Generally, it ranges from 10 to about 100 plus. Rydberg atoms are also hydrogen-like. This means, so if we take a look at where hydrogen is the first atom in the periodic table. It has 1 proton in its nucleus and then 1 orbiting valence electron. Other Rydberg atoms are alkali atoms, meaning they're hydrogen-like. So they're alkali atoms, so they're in this furthest left column of the periodic table. The one that my lab utilizes is rubidium, which is seen right here with atomic number 37. And it is similar to hydrogen. If we think about, if we have a high energy atom and we send that electron to a very far away orbit, we're going to have that valence electron similar to hydrogen, as well as its positive ionic core. This positive ionic core will contain the 36 other electrons, 37 protons, and 45 neutrons.
Yeah.
So Rydberg atoms are really, really cool because they have all of these different scaling laws that scale via n. What this means is that different properties become exaggerated when we go to these high energy levels, which allows us to study different interactions and different quantum mechanics phenomenon more easily. For example, the orbital radius scales by n squared, and the cross-sectional area scales by n to the 4th. These both relate to the atom's size. A good way to think about this is that an atom excited up to the n equals 100 level has an orbital radius of about 0.5 microns. Viruses generally range from about 0.02 to 0.4 microns, which means that this single highly excited atom is larger than most viruses. Other properties also scale by n. For example, the atomic lifetime scales by n to the 3rd. What this means is that for a Rydberg atom, the excited lifetime is generally about 10 to hundreds of microseconds. Now you may think, okay, wait, that's not very long, microseconds, that's nothing. Except for the fact that for the lowest level excited state for rubidium will only live 10 nanoseconds. This means that the hundreds of microseconds we can get out of Rydberg atoms is actually very useful because it allows us to study things and look at them way easier. In addition, the electric polarizability scales by n to the 7th. This is the one that my lab cares the most about. This is because as 2 Rydberg atoms get closer, they'll actually interact with each other. and the positive sides will repel and the negative sides will repel. This is called inducing a dipole moment, and this will add extra energy to our system. This becomes very important when we look at groups of atoms together. So a warning now, this next slide contains the most science that I'll be talking about, but it's really cool science. So I'm going to be talking a little bit about the Rydberg excitation blockade. This is what we're going to talk about when we want to think of a group of atoms. Now, if we send in enough energy for one Rydberg atom, you might think, okay, cool, like we have one Rydberg atom there. But actually, that's not how this works. Because of quantum mechanics, we can't know which atom is actually the excited atom. This means that we have to assume they're all excited, as though it's one collective state. Now, another way to think about this is if we had two atoms. Now, if each of these two atoms share one Rydberg excitation, there's 50% chance that it's this atom and 50% chance that it's this atom. But we can't know which one. That means that these states are entangled. We can't talk about the first atom without also talking about the second atom. Okay, cool. So we put enough energy, we've got that first excitation. Awesome. So now what happens when we want to try to excite two atoms? Well, we find that the energy level is shifted. We can't excite two atoms. This is because of that dipole-dipole interaction that I talked about on the previous slide. Because of those interactions, there's extra energy in the system, and this means that we can't produce a second Rydberg atom. Now, this becomes very important as a way to study different areas of physics. For example, the Rydberg excitation blockade is very useful when we look at quantum simulations or neutral atom quantum computers. In our lab specifically, we actually study how it breaks down and a little bit of properties that actually make the blockade not as effective. But that is a subject for a different talk, so we are going to move on from there. So you may be wondering, okay, so I've learned a little bit about these like highly excited atoms, but I was told that the talk would be about lasers. How are these things connected? Don't worry, they are. When we excite a Rydberg atom up to the n equals 43d5½ state, the size of that atom is 0.116 microns. In addition, the binding energy is negative 0.008 EVs. Now, the binding energy refers to the amount of energy it takes to keep that atom together. What does that mean? So that means is that it takes negative 0.008 EVs to rip off that valence electron, basically destroying that atom. So if we try to create this atom at room temperature, then all of the background gas and vapor around us are moving with some amount of kinetic energy, and that kinetic energy is 0.025 EVs, which is greater than our binding energy. This means that the minute we try and create our atoms, they're too frail to survive at room temperature, so they get destroyed. But if we cool our atoms down to the temperature of about 140 degrees microkelvin, then the thermal energy is about 1.2 times 10 to the negative 8 EVs, which is now significantly less than the binding energy, or the energy that's holding our atom together is. This means that when we create our atom at the 43d5½ state, then it won't get destroyed when we laser cool. So what exactly is laser cooling? So laser cooling is the idea of using light to lower the temperature of atoms. For your benefits, I put up the conversions between Fahrenheit, Celsius, and Kelvin. The one that I'm going to talk about and the one that we care the most about is the Kelvin system. The Kelvin system basically is all positive numbers. And the other thing to know is that absolute zero is the same thing as 0 degrees Kelvin, which is where all atomic motion stops. Those are kind of the bounds of the Kelvin system. So let's look at a couple different temperatures. So the core of the sun, our sun, is a temperature of about 15 million Kelvin, which is equivalent to about 27 million degrees Fahrenheit, which is fairly warm. Room temperature is about 5 orders of magnitude less than that, at about 300 Kelvin or 70 degrees Fahrenheit. One of my favorite fun facts about science is that the ambient temperature of space is about 3 Kelvin, but utilizing laser cooling, we can actually get down to about 10 to the negative 4 Kelvin or negative 450 degrees Fahrenheit. So we cool to a very low level. It's about microkelvin temperatures. You can actually utilize cooling, laser cooling, to cool even further, down to what's known as a BEC, or Bose-Einstein condensate. They can cool down to nanokelvin temperatures. It was first experimentally found in 1995, and it was awarded the Nobel Prize in 2001, which I find very cool. But let's move on to talk a little bit about how objects and photons can interact. So lasers are made up of light, and light is made up of photons, and photons can either be absorbed or reflected. If a photon is absorbed, the object is heated and we're left with a melted snowman. If the photon is reflected, then the photon will bounce back, and due to the conservation of momentum, our object, in this case a soccer ball, will receive a kick in the opposite direction. Now you may have noticed that that soccer ball moved much slower than the photon. That is because the soccer ball is very massive. But this is still not quite a good picture. That's because the soccer ball, in this case, if we shine a light on a soccer ball, we wouldn't move it at all. That's because the soccer ball is just so much more massive than the momentum kicks of the photon. But let's look into the smaller world. Let's look at how atoms and photons interact. So within an atom, there are some natural energy states. Every atom is happy with. So for example, if we have a rubidium atom here and we send in blue light, the atom doesn't really care about it. It just kind of passes right by. But the wavelength of light that the rubidium does care about is 780 nanometer light. So if we send in a photon with 780 nanometer light, we take our atom from the ground state to the excited state, and because again of conservation of momentum, our atom receives a kick to the right. But after a while, our atom is like, I've been excited, but like I don't want to be excited anymore. So it decides to de-excite, or to emit the photon. So it emits another photon, and again, due to conservation of momentum, receives a kick in the opposite direction. So now let's look at how a laser light would affect it. So a laser light means all the photons are going in the same direction. This means when they get absorbed, all those kicks will be in that same direction. But if spontaneous emission, on the other hand, will be in random directions. So when the atom de-excites, that photon will kick it in a random direction, and all of those will average out to 0. Just to reiterate again, the laser photons will all kick the atom in the same direction, and the spontaneous emission of photons will kick the atom in random directions, but all of the random directions will average out to 0. So I'm going to take a step back really briefly and talk a little bit about the Doppler effect. For those who want to look at it, I've included the equation on the right, on the left, but don't worry if it doesn't make sense to you. The Doppler effect is basically the idea where the observed frequency is different than the actual frequency due to movement of either the source or the receiver. In this case, our source, the car, is moving. As we can see, the rings around the car are bunched up towards the front of the car. This indicates a higher frequency in the direction of travel. Whereas on the back end, all of these are spread out farther. Again, this is the Doppler effect. Another way to think about this is the passing sound of a siren. For your benefit, I've included the wonderful sounds of a trumpet being played out of a car. And now listen as the car comes towards us and then is away from us. When the person was playing that trumpet, they played the same note throughout the entire car, but the pitch of the sound changed depending on whether it was moving toward us or moving away from us. Now, the Doppler effect is a very important aspect of laser cooling, so let's get back to it. So, the first thing we want to do is, now that we have this Doppler effect in the back of our minds, is we want to think about the fact that when we actually apply light to our atoms to laser cool, we actually detune our laser beams slightly. Detuning means that we've lowered the frequency of our atoms slightly away from being that direct ground state to excited state amount. What this means is we can use the Doppler effect to our advantage. Because if we have our group of atoms here, and if it's moving towards the right, these laser beams are now more resonant with our atoms, so it is more likely to excite our atoms and drive it back the other way. The opposite is also true. These laser beams are now more detuned, or less likely to excite our atoms and kick them in the wrong direction. This is what allows us to cool in 1 dimensions. But let's expand it to 3 dimensions. So we now apply beams on all 3 directions. So what this does is it makes there be an opposition to motion no matter what direction the atom is moving. Think of this like friction or air resistance. It's a dissipative force on our atoms. But it's very important to note that this is not a trap. We have yet to actually trap our atoms. If our atoms fall out of our beams, there's no way of getting them back. So we employ the first of a set of 2 traps that we use in our lab. This first one is called a magneto-optical trap, or MOT for short. What we do is we have 2 magnetic coils, one below our atoms and one above our atoms. What they do is that the current in the coils are running in opposite directions in what's known as an anti-Helmholtz configuration. This produces a magnetic field of 0 at the center of our chamber with a linear increasing field as it goes out. This allows us to utilize the fact that our atoms will be affected by what's known as the Zeeman effect, which will cause the ground state energies the energy levels to shift in a way that means that the further from the center our atoms are, the more in resonance with the laser beams they are. A good way to think about this is like a position-dependent or restoring force. Imagine that every atom was attached to a spring, and the springs were all attached to the center of our chamber. As our atoms moved farther away from the center of our chamber, that spring wants to pull them back to the center more and more. So that's what's happening. We've now managed to trap our atoms inside the center of our beams and are able to cool them down. But sadly, so this is a picture of our MOT. In it is about 2 million atoms. It's right here, and it's about 500 microns in diameter. A good analogy for 500 microns is really, really finely grained sand is about that size. But our group of atoms are very, very small. So we actually had to employ a second trap due to our needs of our experiment. We needed a larger density, which our MOT could not actually do. So we employ an optical dipole trap. Now the note about the optical dipole trap, it doesn't actually cool our atoms, which is why we load it from our MOT, but it does use 2 things to trap them. It uses high power light and far detuned light. So what does high power light mean? High power light means we send 9 watts of laser light through our chamber. For context, that's a lot because all of our other lasers that we utilize on our table are all on orders of about 50 milliwatts. This is a much, much higher power laser. In addition, we use far detuned light. So that word detuned again, remember that, it means lower frequency. So we use the transition in question likes the wavelength 780 nanometers. The wavelength of light we use for the optical dipole trap is 1064 nanometer light. That means a much lower frequency of light. This means that our atoms are very unlikely to be excited by this laser, but what does happen is we are able to utilize what's known as the AC Stark effect to shift the ground state of our atoms to form this potential well seen here. Now, what this does is when our atoms enter that well, they'll oscillate back and forth as long as the energy depth is deep enough to where our atoms can't escape. The analogy we use in my lab when we talk about the optical dipole trap is imagine a skateboarder rolling down a street, and all of a sudden you pop a ramp around them. If that skateboarder has a ton of energy or our ramp walls are really shallow, the skateboarder will just go right up and out and continue skating. But if either the walls are deep enough or the skateboarder has low enough energy, they'll just get stuck and they'll just oscillate back and forth inside the ramp. The same is true of our atoms. As long as the energy level is low enough or our trap is deep enough, we're able to get our atoms stuck and then have them oscillate back and forth. Now over here is a photo of our dipole trap with a bunch of statistics written on there. I want to draw attention to 2 of them. The first one is the number of atoms, which is about 35,000. Now, as I mentioned before, our MOT held about 2 million. This holds even less. But a good way to think about how small this number actually is that if you think about the smallest bit of dust you can find, generally that's on order of about a mole of atoms. A mole of atoms means 10 to the 23 atoms. This right here is about 10 to the 4 atoms. So it's considerably less atoms, but we're yet still able to control them and confine them and utilize them. The other statistic that I want to draw attention to is the sigma h, which is the width of our trap, which is 7.8 microns. For context, a piece of your hair, so a piece of your human hair, is generally about 17 to 181 microns thick, which means this trap is thinner than your hair. So just an overview. What have we learned today? The first part of our talk, we talked about Rydberg atoms, which are highly excited atoms, and you're able to do really cool physics, especially within the worlds of quantum computing, quantum simulation. We also then switched over to talk about laser cooling. We learned all about the Doppler effect and how useful that is and how important that is. And we also learned that we can cool atoms down to nanokelvins and microkelvins utilizing laser cooling. So I just want to thank my advisor, Aaron, as well as all my past, present, and future lab members, because this lab really works as a unit, so I can't have done any of the science I got to do without them. Thank you.
Yay, Milo.
Yay! Yay!
Yay!
Yay!
All right, so does anyone have questions for Milo?
I can also reshare my PowerPoint if anyone wants to ask.
Yeah.
Yeah, Ronnie?
Ronnie's,
I
yeah.
have a question. How do you get the atoms into the trap?
So
Where do they come from?
we use a vacuum chamber that actually has I think it's a gram of rubidium in one of the sides. It's basically slowly leaking into our system. We use basically an actual source of rubidium that enters into our vacuum chamber slowly just due to vapor pressure. And so basically there's just a lot of rubidium floating around in our chamber. And so when we turn on our beams, there's kind of a bunch just gets collected.
Okay.
Any other questions?
I have a question.
Yeah.
Milo, I have a question. Could you go back to your slides if you can?
Do you have a slide in mind, Fernanda?
In the beginning, the very beginning, as one of the, I don't remember the number, but it's in the intro.
About the Rydberg atoms?
Yeah. When you're talking about the blockade.
Okay.
Hmm.
Yeah, right there. I was just wondering, because since you said, I mean, you have this kind of superposition system where you have one atom in the ground state and the other one is excited and you don't know which one's which. I was just wondering if you could also have the anti-symmetric combination instead of a plus having a minus right there, if that also works, or?
I don't know. I would guess potentially, but the probability of either one of those would be the same. The probability of either having the plus there or the minus there would still have the 50-50. But I don't know if that would be then added in as different terms. Aaron, if Aaron or Paul, if either one of you knows the answer, you can also chime in. No, okay. But yeah, I'm not sure.
Yeah, that's correct, Milo. You could get either one. You could get the symmetric or the anti-symmetric. Sorry, it took me a minute to unmute.
No, you're good.
Thank you.
Any other questions?
So Milo, now that you've done this research, can you help us to understand what would come next? If one were going to continue in this line of research, what would one investigate next in order to continue to make a contribution to science?
As I mentioned before, I didn't actually cover a lot of the direct project that I was working on. I was working on this process known as state mixing, which breaks down this blockade picture. So we actually have a lot. We actually have about we're just about to get a paper out in my group, but we actually kind of know where we're headed. We're gonna continue to look at the same phenomenon that we're seeing, but I can also talk about that later because that requires a lot more background information about like state mixing and how that works to discuss.
Okay, you can tell us over dinner.
Hmm.
I think we still have time for more questions.
Oh, Milo, can I ask a quick question?
Yeah, Max.
So when you were talking about how cold you need to make your trap,
Yeah.
It seemed like you needed it to be below the binding energy of the Rydberg atoms,
Mhm.
but it seems like you made it excessively more cold than it actually needed to be. Can you talk more about why?
Yeah, so we actually cool down. So 140 microkelvins is the Doppler temperature for rubidium. It is kind of through this process, that's the temperature that you get out at the end, because just kind of through this kind of laser cooling, like you just kind of cool down to this temperature. I don't think that there would be a way to necessarily like have a warmer temperature. And also, for the most part, you actually don't want a warmer temperature because the lower the temperature, the higher the density of our atom cloud is, which is really important for us. But I wouldn't, yeah, so we cool down to the Doppler temperature, which is just kind of the temperature that this process gets out.
Okay, thanks. So it's like the place you end up.
Yeah. We actually, instead of our system, we now actually cool colder. We cool down to 35 microkelvins now, but that's through a different kind of process that I didn't talk about today.
Cool. I think we still have time for like one or two more.
I have another question, but like I don't want to monopolize all this time. Is it okay?
Go ahead, Ron.
Go for it.
Okay. Why, like, bigger picture, why are you doing this research?
Yeah, so as I said before, the Rydberg excitation blockade is really important for areas of research such as like quantum computing, or like say for example a 2-bit quantum gate, which is basically where you isolate two atoms and you use them to basically talk to each other. And the process that I'm looking at that breaks down the blockade is kind of one on a long list of potential problems with these kind of experiments. And so our goal is to kind of characterize and really understand how this specific process breaks this blockade down, which will allow researchers who have slightly different system setups to basically say, okay, I'm running in this regime, which because of that group, we know means that state mixing isn't a problem. Or on the other hand, like we're running in this regime, which means we definitely know this is a problem that we have to think of another workaround. So basically this is a way to characterize one small aspect of the blockade for those who want to utilize it in different ways.
All right. Thank you again, Milo. Yay.
Yay.
Awesome. So I guess it is now my official pleasure to introduce our second speaker, who will be Georgia Stolle-McAllister, who is a physics major and Russian minor graduating in Kenyon in 2020. She hails from Baltimore, Maryland. And the research that she's presenting on was done under Philip Muirhead from Boston University, as well as Paula Turner from Kenyon. So floor's turned to you.
Okay, so today I'm going to tell you about some research that I've been working on this past year with Professor Philip Muirhead from Boston University and Paula Turner at Kenyon. And this started as an REU project last summer at the Mariah Mitchell Observatory. I'm going to tell you stories about stars. So first of all, the stars that you see, if you go out at night and you look at all those stars, it's pretty surprising, but about half of those are actually binary stars. So there's actually another star there. It's a binary star is a system of two stars that are bound to each other by gravity, and they're orbiting each other. So it's pretty incredible. About half of them are actually in this type of system. Another fun star fact is that there are some stars that are variable stars. So this means their brightness is changing over time. And this is not like when you look at the sky and stars sort of twinkle or shimmer. That's just from the atmosphere getting in the way. But variable stars actually their brightness significantly varies over time and is generally periodic. And there's lots of different kinds, but the two main categories are whether they're intrinsic variables, so there's something inside the star that's making them vary, or extrinsic, which is something on the One famous example are the Cepheid variables, which is what the picture on the right here is of, where these types of stars are actually, their radius is getting bigger and smaller over time, and so their brightness is changing. So that little fuzzy dot in the middle starts out bright, and then it gets dimmer and dimmer and dimmer, and then it gets brighter and brighter again, and it'll just keep going like this. So these are some types of variable stars. Another type of variable star, a fun one in particular, is called Algol, also known as the demon star. So Algol is a very bright star in the constellation Perseus, and it varies so significantly, and it's so bright that you can actually see it vary with your naked eye. So if you go out over a period of several hours or a couple of days, you can sort of compare it to the stars around it and see it change in brightness. And people have noticed this for a long time. So since the time of the ancient Egyptians, people have kept track, have noticed that Algol varies and kept track that it varies about every 2 days. But they didn't know why, and so people assumed it was bad luck and it was an ill omen. And my favorite is that it actually, in the constellation Perseus, it marks the eye of Medusa. So there's the Greek story where Perseus kills the Gorgon Medusa, who can turn you to stone by looking at you. And so since Algol is its eye, Medusa winks at you about every 2 days. So watch out. But people didn't know why this star was varying for a long time, until in 1783, an amateur astronomer in England named John Goodricke was the first one to correctly propose the reason for why Algol was varying in brightness. And he said, well, maybe there's a dimmer object that's going in front of it periodically that's blocking that light. And it turns out he was right, and the dimmer object is another star. So Algol is actually a binary star. There are 2 stars there, and they're going around each other in such a way, they're lined up with us in such a way that the stars periodically go in front and block each other's light. And this is what an eclipsing binary star is. So this is an extrinsic type of variable star because it's not something inside the star that's changing. It's just the fact that there are 2 of them, and we're lined up and with them, and so they're blocking each other, and they're creating eclipses. So just a quick review of what are eclipses. So we can see eclipses in our own solar system, where, for example, a lunar eclipse, because eclipses are just basically shadows. So a lunar eclipse is when the Earth is casting a shadow on the moon. It's getting in between the sun and the moon, and it throws this shadow on the moon. And then the other way is a solar eclipse, where the moon is in between the sun and the Earth. There was a full solar eclipse that went across the United States in 2017. So some of you might have gotten to see that, where the moon was casting its shadow on the Earth. But this also happens on faraway stars. So 2 stars that are orbiting each other, even if they're very far away from us, if we are lined up with them, then we will see those stars go in front of each other and cast shadows, and we can see those shadows. So this is just a quick little animation of a binary star, where you can see, if this is from our point of view on Earth, the stars are periodically go in front of one another. And this is the whole thing. This is what makes an eclipsing binary star an eclipsing binary star. This is all it is. But it turns out that eclipsing binary stars, even though Algol was named the demon star, turns out they're actually really important and useful tools in astronomy. Because from eclipsing binary stars, we can measure these properties of stars that are otherwise very hard to measure. So things like the radius of the stars, so how big they are, the shape of the orbit, like whether they're going around each other in a nice, neat circle or around each other in this big, stretched out oval. We can also see how fast the stars are going around each other, and it provides a way to measure the mass of each star directly. So these are all things that are really important to know about stars, but really hard to measure. And it just happens that eclipsing, the orientation of an eclipsing binary star allows us to measure a lot of these properties. So they're really useful. And one of the ways that we are able to make some of these measurements is with what's called a light curve. So a light curve is basically just keeping track of light over time. So if you had just one plain star sitting by itself, not varying, just shining, and you made a light curve, it would just be a flat line all the way across. So it'd be a kind of a boring light curve. But eclipsing binary stars have these dips in their light curve. So if you're looking at this diagram, we're going to say that the orange circle is the brighter star. It's not necessarily true that the bigger star is brighter, but this is just how we're taking it for this diagram. So the orange one is brighter and the red one is dimmer. So when we see both of the stars, we get all of the light from both of them, and that's the most light we get. And then as they go around each other, at some point, the dimmer star gets in front of the brighter star, and we get what's called the primary eclipse. So this is like the darker shadow. Then they go back around to being next to each other, we get all the light, and then the dimmer one gets blocked. And so we get a shallower eclipse, and this is the secondary eclipse. So the particular star, I've been studying this year, I've been studying a particular eclipsing binary star, and its name is FL Lyra, and it's located in the constellation of Lyra, which pretty soon, if you go out at night, you can look up and you can find the summer triangle, which are three bright stars that you can see at least in the northern hemisphere during the summer. And FL Lyra is it's right off the edge of one of the sides of the summer triangle. So this is one of the edges this is the constellation Lyra, the very bright star Vega, and then Deneb, which is in the Northern Cross over here. And FL Lyra is just off to the side. But you can't see it with your naked eye. It's not quite bright enough. You can see it with a telescope. So last summer, I was working at the Maria Mitchell Observatory, and I got to use their 24-inch optical telescope to take pictures of this star. And this is one of those pictures. And that one dot of light inside the red circle, that's FL Lyra, and it's actually 2 stars, even though it's just looks like 1 point. There are 2 stars there. So why do we want to study FL Lyra in particular? One of the reasons is that FL Lyra is very similar to the sun. So FL Lyra has 2 parts, but each of the stars in that system are really close, are very similar to the sun. So one of them is just a little bit smaller in terms of mass and radius, and the other one is just a little bit bigger. They're also similar in terms of their type of star. So on the right here is what's called a Hertzsprung-Russell diagram, or an HR diagram. And this is a way of categorizing stars. We can measure the luminosity, which is sort of the brightness, and that's on the vertical axis, and also the temperature. And there's a couple ways of measuring that, but that's on the horizontal axis. And if we measure these for lots of stars and put them on this plot, we get a pattern that looks like this. And the main sequence, which is that stripe right through the middle, that's where our sun is. So our sun is basically where those yellow stars are, right around here. Our sun is a pretty average, normal, basic star in the middle of its life. And so is FL Lyra. So FL Lyra is also right up here on this plot. And our sun, so it's similar to our sun, right? This is one of the reasons we're interested in it, because our sun we can study really well because it's so close to us. So we can measure properties of the sun so for example, you can look at how the planets move around it, and we can measure the mass of the sun. We can get the radius, and we can also even take images like this where we can see the surface of the sun. And the picture on the left here, there's a little black dot up in the top left corner, and that's Venus going across the sun. So that's an entire planet. And then compare that to how much detail we can see on the surface. So this is pretty amazing and great for the sun. But any other star is too far away to do this. So any other star just is a point of light. We can't resolve the surface like we can for the sun. And so they're harder to study, they're harder to learn about, but we want to know about them. And we can learn about them if we use telescopes. So one of the telescopes that I got to use data from for this project is the Kepler Space Telescope. So putting telescopes in space is great because you get above the atmosphere and you get nice, precise, clear data. And the Kepler Space Telescope launched in 2009, and it was meant to look for exoplanets. So it's looking for planets that are going around other stars. But it does this in the same way that we study eclipsing binary stars, because when a planet goes in front of a star, it blocks some of its light, and so we get a little dip in the light curve. So the data that Kepler collects is great for eclipsing binary stars as well, and this is another reason that we want to study FL Lyra in particular, because it happened to be in this section of the sky that Kepler observed for 4 years. And actually, Kepler, after its 4 years, there was a part of it that broke, and so it couldn't keep looking. Its mission was to look at this one little patch of sky that was about the size of your fist if you hold it up to the night sky. But it broke and it couldn't keep looking at that, couldn't keep itself tilted to look at that section anymore. But NASA was like, well, this is an expensive telescope, we're going to keep using it. So they repurposed it, and it kept working for a long time, and it still looked for exoplanets, but it also looked at Neptune and I think asteroids. And then it ran out of fuel in 2018 and it was decommissioned. But we get to use the data from the first 4 years, and we get light curves that look like this on the right, which are nice and smooth, and it's nice, precise data. The other space telescope that I got to use data from for this project is called TESS. So this is the Transiting Exoplanet Survey Satellite. And it was basically, it's doing a very similar thing to Kepler. So this was launched in 2018, and it is also looking for planets going around other stars. But TESS is actually covering about 85% of the sky, as opposed to Kepler, which just looked at a little patch mostly. And TESS observed FL Lyra last year, at the end of the summer last year, into the fall for about 2 months. So this is great. We get to use all of this nice space telescope data. It's wonderful. And when you have really precise data, you end up with some surprises. So it turns out that over the 4 years that Kepler observed FL Lyra, there was this weird trend in the light curve. So the primary eclipse of FL Lyra, which is the part where the brighter star is being blocked, right? That's the deeper eclipse. It's getting deeper over time. And then the secondary eclipse is getting shallower over time. So this is weird, because if you have two stars, they're going around each other, why are their depths changing, right? But the trend is there. So this was my project, was to try to figure out, is this still happening? What kind of pattern might it follow? Like, is the primary eclipse getting deeper and then getting shallower again? And also, why is this happening? So what could be causing this? And there are a lot of options. So when in an eclipsing binary system, there's lots of things that can affect how the light curve looks to us. So for example, the radius of the stars will affect what that light curve looks like, how close they are to each other, how their orbit is tilted with respect to us, all kinds of things. So the way to try to figure this out is to use models. And we can put in all of this information about things like the radius of the stars and the inclination of the orbit. And we know how the physics should work, and so we make a model. And then we can compare that to the Kepler, to the actual data. And you can see just a quick example of a model. The top here is flat all the way across, because this is sort of an ideal system, but the actual data has this wiggle in it, and so that is challenging for trying to fit to a model. So what we do is we make lots and lots of different models. So we try out all different parameters and we compare this model to the data over and over again, and we find the one that fits the best. And this is how we measure the parameters of the system, because when our model fits that data really well, we know that then those are the parameters that are making the real light curve look how it looks. And it turns out that after I did this for lots of different parameters, most of the parameters didn't change over time. So for a couple of examples, the top left here is the radius ratio from the Kepler data over 4 years. So this is the ratio of the sizes of the two stars. And this is pretty much constant over time. This is just basically a flat line. The same goes for the angle of inclination, which is how much the orbit is tilted towards or away from us. So like whether we're looking straight along the edge or it has a little bit of a tilt to it. And this is also pretty much a flat line. There's a few outliers in there, but it's pretty steady. The only thing that changes significantly is the surface brightness ratio. So this is how bright the stars are on the surface compared to each other. And this changes a lot. So all of these plots have the same, they're all ratios, right? But they all have the same sort of scaling on the side. It's all a 0.1 difference from the top to the bottom. So you could really compare how much this has changed. And so this is pretty exciting because we can see something that has changed. And if this is the only thing that has changed, only the brightness ratio varies and all the other stuff stays constant, then that means it sort of suggests that that weird trend we saw in the eclipse depth should be caused by this brightness ratio change. And that is something on the surface of the star, which points to the possibility of studying the activity cycle on the surface of the star. So what is an activity cycle? The activity cycle is caused by magnetic fields sort of sloshing around and in the sun and in stars. On the sun, we can see it really well because the sun is close to us. So a couple of features of an activity cycle are one is sunspots, which are these darker, cooler regions. Faculae are brighter regions, and then there's also things like solar flares. So all of these are caused by magnetic fields sort of sloshing around. And it turns out that on the sun, this activity cycle is very regular, and we can look at the number of sunspots over time, and it has a very regular cycle. So this is a plot of number of sunspots over time. And you can see it's very periodic. Like it just keeps repeating at the same way. And this is about an 11-year difference. So about every 11 years, the number of sunspots gets to a maximum and back to a minimum. And we have lots of data on this. We can track it over time. And this is really interesting that it happens this way on our sun. But we don't know how this works on any other stars. Like, is this happening on FL Lyra? This is what we want to know. So how is it working on other stars? And like, is it similar? Does it have a cycle like this? Is it somehow different, right? We don't know. Okay, so what I want to leave you with is one is that eclipsing binary stars are really important for learning about stellar properties, because just the way that the eclipsing binary stars are lined up with us, we get to see their shadows and we can make a light curve. And from that, we can learn things about like their radius and their mass, which are generally very hard to measure on stars, but we need them. We want to know about these things, and we can use from eclipsing binary stars, we can measure these and then use them in models for all the other stars that we can't measure so well. The other thing is that we have an activity cycle on our sun, and it's very regular, and we can see it, we can observe it on the surface very clearly. But we want to learn about the activity cycles on other stars, because if we only know about the activity cycle on our sun, like that's only one star. There's a lot of stars out there. So how does that work on other stars? And we also still have questions about how it works on our own star. So if we can start to get data on what activity cycles are like on other stars, we might be able to learn a little bit even more about our own. And the project that I've been working on is a way to use eclipsing binary stars that might actually be able to tell us about the activity cycle on some of these distant stars. Because in the end, what we're trying to do is we're trying to learn about other stars to the same extent that we know about our own. Because we can see our sun, we know a lot about it, and we want to learn about other stars the same way. And if we do that, we also will have a better idea of how our sun works and how stars in general work.
Mm.
All right, so I just want to quickly thank Professor Phil Muirhead from Boston University, who advised me through this whole project. Paula Turner from Kenyon for, of course, always being my advisor. The Kenyon College Physics Department, you are all wonderful. And then the Mariah Mitchell Association, because I started this project as an REU project last summer at the Mariah Mitchell Observatory.
Oh,
Thank you all.
sweet.
Awesome. So we now have time for questions. If anyone has a question for Georgia.
You did it.
Okay, I can start with a good question, get that ball rolling.
Sure.
So you talked all about the solar. Actually, I want to talk about the eclipses. What happens? Like, could we see anything if, say, if the binary stars were eclipsing like this? So we were staring kind of front face at it, or would we not see any changes of any kind?
No, so we only see it as an eclipsing binary star because we happen to be in line where they're crossing each other. So there are lots of binary stars out there that are orbiting each other just normally, but we happen to be oriented so that, like you said, like if we're looking at them from this perspective, we don't ever see them cross each other. And so we wouldn't be able to actually see eclipses. We could maybe figure out it's a binary star from other ways, but we might not even ever know that there's a binary star there.
Cool. Any other questions for Georgia?
Can I ask a question, Milo?
Yeah.
So Georgia, is there any way to detect these binary star systems other than seeing that one object appears to sort of twinkle, like sort of vary in intensity? Like, what are the other methods we have to determine that this one spot in the sky is actually a binary star?
Yeah, so there's a couple different kinds of binaries. One type of binary just is the optical binary or visible binary. So you can look at it with a telescope and see two stars. So that was like the example on the first slide, which I think I forgot to say, but those two stars in that image are Alpha Centauri A and B, which is the next closest system to us other than the sun. And those you can look at with a telescope and resolve two different stars. There's also, you can also figure out that something's a binary because if there's two stars orbiting each other, at some point, unless they're exactly lined up to be going like this with respect to you, at some point one's going to be moving towards you and the other one's going to be moving away. And so we can use the Doppler effect, which Milo told us about, by looking at the absorption lines from these stars and seeing where we expect certain lines to be, and they'll be shifted periodically back and forth to like higher wavelengths and lower wavelengths. And so we can tell then that this star is moving towards and away from us periodically. There's also some systems where you can look at both of them and take a spectrum, so look at all the different colors of light coming from those stars, and they have, if they're fairly different types, they will have different sort of signatures, sort of thumbprints from what elements they have in them, and then you can see that like there are two stars there, maybe, rather than just one.
Yeah, great answer. Thank you.
Yeah.
Cool. We have time for one or two more questions if anyone else has one. We got two questions. Perfect. Either one of you can start.
Leah?
Okay, I'll go. With these stars, do they all have to be in like the same range of brightness? Like you showed us that chart that had stars like like this, and then they had like the supernovas, I think, and then like the white dwarfs. Can you have eclipsing binary stars that like are a mix of those ranges, or do they always have to be kind of in the same range of brightness and size?
No, so you can have a mix. That's a good question. So Algol actually is the demon star is actually a mix of two different types of stars. Yeah, so you can have a mix, and sometimes having different stars makes it easier to tell that there's a binary star there. And if you have, it also would change the shape of the light curve. So the ones for Kepler, the ones for FL Lyra, because those stars are so similar to each other in mass, it makes that really smooth sort of eclipse depth. But if you had two very different sizes of stars, when they crossed each other, you would get a flat bottom on the eclipse because you'd have a long period of time where one was being totally blocked by the other. Whereas FL Lyra, because they're about the same, you only get like an instant where they're actually totally blocking each other before they go back up.
I have a question.
Yeah.
How far is that star away from the planet Earth?
So I think it's about 40 light years away. So it takes light about 40 years to get to us from that star. I should check that though.
How would the activity cycles change if there are different types of stars?
That is a good question, and I do not know the answer. That's one of the things we're trying to sort of learn more about. We do know that so because activity cycles are caused by magnetic fields sloshing around, when you have a binary star, we expect that the activity cycle will be more active, like more things will be happening, because as these stars are going around each other, they're generally moving faster because they're pulling on each other, and that faster spinning and moving around sloshes things around more. But I don't know how having different types of stars would change that theoretically, but it probably would.
My question was also about the activity cycles and its importance, but I think your answer just answered my question.
Okay.
Awesome. With that, we are at time. Thank you all for coming to our talks. We appreciate both the support as well as the interest. It's not very often we can get people who actively want to learn about what we're doing, so that's always really, really exciting. So thank you again for all coming and listening to us talk.
Yes, thank you all so much.
Yay! Thank you. Yay!
Well done.